Good day and welcome everyone to the Coastal Resiliency and Sea Level Rise, Managing New Concerns During Remedy Design conference call hosted by Scott Hartzell. My name is Nandi and I'm your event manager today. During the presentation, your lines will remain on listen only. You may submit a question on WebEx. To do this, please click on the three dots at the bottom of the screen, then choose the Q&A tab, type your question, and click Send to all panelists. As there will be videos played during today's call, kindly make sure your speaker is turned on and your headphone is plugged in. If you require assistance at any time, please key *0 on your telephone and the coordinator will be happy to assist you. I would also like to advise all parties that this conference is being recorded. And now I would like to hand over to your host, Scott. Please proceed.
Thank you very much. Welcome, everyone. Appreciate you all being on the call today. We have a presentation that not only is going to be very interesting and informative, but from my understanding, the word virus does not appear anywhere in the next 60 minutes. So you can sit back, relax, and prepare for a very good presentation. Our presentation today is titled Coastal Resilience and Sea Level Rise, Managing New Concepts During Remedy Design. Our speaker today, Dr. Shamsul Chowdhury, is a professional civil engineer with Parsons. He brings to us over 35 years of experience in coastal engineering and water resources engineering work in Canada, in the United States, in Japan, the Middle East, and in Bangladesh. You can go to the next slide. A few of our standard housekeeping items. Your lines are muted, but you can use the chat feature in WebEx to present a question, which will be held until the end. We will have a short Q&A session, 10-15 minutes at the end of the presentation, and we would ask that you would give your name and location when you ask a question in case we need to follow up with you afterwards. Go ahead. As a brief agenda, the presentation and the presentation with a little bit of Q&A time at the end, and we'll go ahead one more. Our speaker, Dr. Chowdhury, with the BS degree and master's PhD and in BC and Manitoba. I'd like to turn it over to Dr. Chowdhury now.
Thank you, Scott. Today's my presentation is on the coastal resilience and sea level rise, managing the new concept during the remedy design. At Parsons, we operate with the 6 core values. My presentation is focusing on the innovation and safety. So we will discuss today mainly about the sea level rise and some modeling, the coastal modeling and the wind-generated waste modeling and the storm surge and resilience housing. So first of all, what is coastal resilience? Resilience is important for all communities facing hazards such as flooding. Coastal area have additional hazards risk from storm and tsunami, making the resilience particularly important in those locations. We cannot overrule the mother nature, but we can take together to build resilient communities. Coastal resilience means building the ability of a communities to bounce back after a hazard event. So if you look at these pictures, so we can see this is before the storm, during the storm, and after the storm is a damage. And this is the bounce back, this process is the coastal resilience. So the question is the sea level rising? The answer is yes, sea level is rising. So it has a lot of factors. So most of the factors is the ocean temperature, atmospheric temperature. The higher sea levels means that the deadly storm surge push further inland. Then that once deep, which also means more frequent flooding and the shoreline erosion in that area. So this sea level rise in British Columbia, BC, this is published by NRCan. So this is the Port Hardy and the Euclid and the Port Renfrew and the Victoria, Vancouver Island and the Vancouver here, and this is the Vancouver Island. And if you look at the sea level rise for the different location, is the Port Hardy, you can see with the 2100 is about 0.67 meter, this area. And Port Renfrew is about, say, 0.7 meter. This point Renfrew is right here, and Euclid is almost the same. And the Surrey, 2100, we're expecting about a meter. It's right here, is the Vancouver. So this sea level rise policy card for Vancouver, Canada. So this is the sea level rise policy for Vancouver. So we have been using for next 100 years, the sea level rise will be 1 meter. This is the number we have been applying for the coastal structure and the waterfront waterfront structures. 1 meter for next 100 years. I mean up to 2100. Because this curve is started from 200, so this is the 100. And the sea level impact, current and the future. For example, this is the current sea level is right here, and the future we will get the more higher water level, sea level, I mean. So what is happening, we will lose this shoreline, and we lose the waterfront structure and the driveway also. And due to this sea level rise, we will get the more runoff and inundation this area. This is one example here. This is the Lulu Island, Vancouver International Airport, and this area we have a dike is about 5 kilometer long dike, and is the community right here, and the wave is coming from these directions. So this dike, maybe we need to increase the elevation in the future because the sea level rise is increasing, and the wave runoff and overtopping also increase. So next slide, I will give you the better picture for this area. So this is the present dike elevation, and the sea level, present sea level right here, king sea level right here, king tide. And in this condition, if we expect the runoff height is up to here, in the future, we will have the higher sea level right here, and the king tide will be more than that, above that, and we will expect more runoff and overtopping. So this area will be flooded. So there is one process, one mediation, maybe we increase the dike gradually with respect to the sea level rise. So if you look at the picture right here, so this is the present condition, and gradually this area will be inundated in future if we don't increase the elevation of the dike, or if we don't do any offshore structure to dissipate the wave energy. Next slide here. So I will tell about the tsunami inundation model. So this is the model, this is the domain, this area. So it's about 2,500 kilometer by 2,600 kilometer. We have developed a model for the Cascadia earthquake. When we will have the earthquake, well, this area will be inundated. So how much will be inundated? So we have estimated from the model. So I'm going to present the model here. So first of all, what is the cause of tsunami? Most tsunami are caused by major submarine or the coastal earthquake, which lift the seabed, causing a column of water that rise the ocean surface. The tsunami also caused by the landslide, but in our case, we're considering the coastal earthquake. So if we look at the history of the Cascadia zone earthquake, last we have an earthquake in January 26, 1700, West Vancouver Island, and the magnitude was 8+. This is a great earthquake. And the last 1964, we have the earthquake 9.2 in Alaska, and we had the inundation in the Port Alberni is right here. So from here, the tsunami also arrived in these locations. So the Cascadia subduction zone, the two oceanic plates right here, one is the oceanic plate and another is the American plates. So these two plates are moving, but now this two plate is locked, and this the oceanic plate is pushing down like a 4 centimeter per year, and the stress is developing right here. I will show you a video. You will get a better picture from this video when the earthquake will happen, how the tsunami will generate.
We have no idea why it doesn't make an earthquake tomorrow, next week, next year. It should, but it doesn't. Cascadia can make an earthquake about 30 times more energetic than San Andreas.
The Cascadia subduction zone runs some 700 miles from Cape Mendocino in California up to about the middle of British Columbia's Vancouver Island. It's an offshore plate boundary where the oceanic plate is diving underneath the North American plate, forcing it to crumple back like a spring. Eventually, that energy will release, and the North American plate will thrust forward and down. The outer margin of the plate will form a hole in the ocean that will become the leading trough of a tsunami.
So this is the cause of the tsunami in the Cascadia zone. So if you look at the history, say last 10,000 years, so we can see about the 40 earthquake is happening in the Cascadia zone. This the number is provided by the scientists and the geologists. They have taken about the 50 samples from the Washington, Oregon, and the California. Then they come up with this graph. So we can see that mostly the greatest earthquake is between the 8 and 9 magnitude. If we do the more analysis, we can see the 8.0 plus magnitude of earthquake is happened every average. This is the average number, 246 years, and 8.5 plus magnitude of the earthquake is happened every 500 years. This is the average year. The last earthquake we had 1700 and present like a 0. So 0 year if we consider. So the last one is happened 320 years ago. So right now, so this earthquake is due. It may happen anytime, but we don't know because based on this number, 246 and 500 years is just in between. So we don't know it may happen any time. So after the earthquake, what will happen? If you look at this video, I will play this video, and Dr. Bryant is the USGS geologist. He did some investigation, and he found some subsidence.
In this region, it down dropped. Hilltops, valley bottom, everything got dropped down by, say, 5 feet. The first thing that the spruce spot saw was the tsunami marked by the tsunami.
And that salty water makes it difficult or impossible for these trees to exist.
These are plants that are not adapted for that kind of life.
Do you believe the Cascadia subduction zone will release energy like it did in 1700 again?
It's a process that's been going on for a long, long time. So just because you and I are here doesn't mean it's going to stop.
So this is a process has been going on last many years. And this is the same thing as the schematic diagram when you have the plate locked. So this is uplift and this is a subsidence. And we are expecting the Vancouver Island will be jacked down about 1 to 2 meters. So if we do the model, what the model will tell us? It tells us where we are the most at risk and the extent of that risk and estimate time from the earthquake to first and subsequent wave at the site. It helps us to determine the type of planning we should do. It shows us that what might expect to see in the specific locations. So when you have done developed a model, we use a couple of design criteria. So definitely is a hydrodynamic model. And we have used the 2,500 by 2,600 kilometer domain, and the water surface, high water level plus 100-year sea level rise, and the 500-year probabilistic subsidence, which is provided by NRCant, incorporated in our model to develop the tsunami. And this is the equation. I'm not going through this one for the shallow water equation to develop the model. So in our model, so close to the shore or close to interest point of the community, we have used the very fine mesh, the high resolution mesh to get the better result, and the rest of the area we use the coarse mesh. So after developing the model, so we have calibrated the model with the Haidegua. It's the 2012 is the earthquake, the Haidegua. We have collected the information and location from the USGS and developed the subsidence in this area by the method of Okada and compare with our model to calibrate the model so that once the model is calibrated, we have applied that one in the Cascadia zone. So this is the Haidegua, and there was an earthquake in 2012, 20th of October. And this is a Winter Harbor. There is a gauge station, and the Tofino, there is another gauge station. It records the water level after the earthquake. If I play the video here, you'll see the wave is propagating, but there is no audio for this one. So you just look this one. After the earthquake, you can see the wave is propagating, and it crossed the Haidegua, and it crossed the Tofino. It's crossing right now. So from the model, the height of the wave for this area and the height of the wave in this area, we compare from this station with our model. So Winter Harbor is the Winter Harbor. The wave amplitude was 15.6 centimeter, and from our model, we obtained is the 14.5 centimeter. And the Tofino just 7.5 centimeter, and we got it 8.0 centimeters, which is very close number. So we can say this model has been calibrated. Now we apply this model for the Cascadia zone. So this is the subsidence provided by NRCan. So if you look at here, this is the Vancouver Island here, and this is the blue one. This is the -2 meter, -1 meter, and 0.5 meter. So we can see there will be the subsidence in this area between 1 and 2 meter during the earthquake. And this area will lift up, and this area will generate the tsunami, and the tsunami will propagate this direction, and this direction, and this direction too. And after incorporating that subsidence, this is the bathymetry. So this is quite a deep area right here, in the deeper, in the shallower right here. This is just the bathymetry. And in our model, so I'm going to present today about the two sites. One site is right here, another site is right here. So close to the site, as I mentioned before, we use the fine mesh, and the rest of the area is the porous mesh. So this is the whole model after the earthquake, how the wave will propagate this direction and all around what will be happen. So you can see the earthquake has happened. I consider this time is just a dummy time is the 3 hours 1 second, and then we can calculate. We can see how long does it take to arrive the earthquake. The tsunami towards the land or the shore. So there is no audio. You can see after the earthquake how the wave is propagating. It's just a quick motion. So if I make it slow, so you can see if we have the earthquake, say 5 minutes, 3 hours, 5 minutes, it will take about 40 minutes to arrive with the tsunami, the Vancouver Island. It's very fast, 40 minutes to 15 minutes is the wave tsunami will be arrived in Vancouver Island. This is from our model. And as I mentioned, this is site number 1. The site number 1 is right here. So we have done the tsunami model, and we have estimated how far this community will be inundated. This is the aerial photograph for this community. You can see this is the very low area, and this is the community is also compared to high area compared to this one. And the next slide, I will show you from the model how we estimate the inundated zone. Because it is a low area, and we consider the high water level plus sea level rise, 100-year and 500-year probabilistic displacement in the Cascadia zone. So the earthquake has happened. It takes a little bit time. Yeah, water is moving. Little bit time to come the first wave and the second wave. $40 minutes. Yeah. $50 minutes. Then you can see about 1 hour it takes to arrive the highest wave in that area. And then this wave is gone. Again, the third wave is coming. Based on this information, we have identified the inundation zone from the tsunami for the community. Next slide. Okay, I can, yeah, this is the worst one, yeah. From that model, we identified the inundation zone for that particular communities, and we identify also the lift station and all the infrastructure should be relocated, including the communities, because during the tsunami, this area will be inundated. It's not good to stay in this area. Second site, this is the site, the Port Alberni area. And because if I show you the full model, is very small. So I just cut this small area and blow this area right here, blow out this area. You can see this is the marina right here. This is the marina. And during the tsunami, this is the way the water will be flowed through the buildings, yeah. This is just the flow vector and the inundation. This area is low, this area will be inundated. And this might be, there's a couple of streets, and the land will be inundated, yeah. Next question will be, what is the speed of the tsunami? It's very high speed of the tsunami. It depends on the water depth. If the higher water depth will have the higher speed, and when it's coming the shallow, and it will lose the speed and the wavelength, and it will be higher and higher. So this is, here's the example. In the if the tsunami occurs like a 15,000 feet, and the speed will be about 500 miles per hour. So when it's gradually coming to the shore, it's losing the speed and it will break. Yeah, this is the same calculations. If we have the 200-meter water depth, you will get the 159 or 160 kilometer per hour. Yes, it's right here. So this is tsunami is very high speed, but if we stay in the deep water, it's very hard to feel the tsunami because the wave height is not very high. Only the wavelength is high, longer. So next will be we have the high water level, and we know the sea level rise, and we need to include the storm surge. When we have the storm, there will be the storm surge with the push by water, pushed by wind. It's a simple example. If we don't have the information about the storm surge for a particular area, we can make a model, and based on the wind information, historic wind information, and we can come up with a storm surge at the particular locations. So storm surge in the deep water is less than compared to the land. So this is an example. The storm is moving up here. So you can see this, the initial water level was 3 meter. I think the 3.2 meter. And when the storm is coming, close to the shore, this is the number is right here, 3.8 meter, which means that we have the storm surge is about like a 0.8 meter of the storm surge in this area. Yeah, so we have to include also this storm surge in the model to estimate the inundation for that particular area, because the coastal storm surge is often the greatest threat to life and the property. Again, it's just a storm. Just wanted to show you how the wind field is moving when we have the storm. The wind field is moving around the high storm. So now we know the high water level, sea level rise, and storm surge. If we have the storm, then the wave will be generated, and this wave will be propagated close to the shoreline. And from that wave, we have identified the inundation zone based on the wave height and the wind speed, what is the type of the, so how far that the inundation zone will be. So if we do, this is a model from the wind generated wave. So when the wind is blowing from the north towards this area, it will generate the waves for this area. And there is a dock right here. So you can see this is the blowout part here. Since the wave in this area is about 2 meters and behind the dock is less. And this wave will be run up in this area. That will be another calculations to identify the inundation for this area. So this can be possible, yeah, to calculate the inundation from the wind and generate that waves. So next example, the wave height, as I mentioned earlier, is the Lulu Island, and there we have the dike right here, about 5 kilometers, and the wind is coming from northwest. And we are expecting the wave height about 2.55 meter wave without any structure. So why we are getting the higher run up? Because if we have the mean sea level right here, our wave is breaking right here. So when you have the higher sea level rise, so wave will break close to the shore, close to the structure, and it will overtop. So that's why we'll get the higher overtop. This is the picture from Japan. And in Japan, they have that always most of the structure is the offshore structure because they dissipate the energy first right here, and then small wave will propagate. They will get the less wave height. And this is also another type of submarine structure. Is called the submerged breakwater right here. So wave will be arriving here and it will break, and the transmitted wave will be propagated. And when you place this type of structure, between this dike and this structure, this sediment movement and the flow pattern will be changed. So that should be taken care of in the model, which area will be the best and what is the size of the breakwater. So that can be done by considering the model. So if you look at if I place a breakwater, a couple of breakwater in front of the main dike, so outside of the breakwater, we have the 2.5 meter, and inside the breakwater, you can see this, the wave height is less, so which means that we'll get the less run-up and overtopping and the less, the dike elevation. So that can be we can look at the flow pattern inside this zone. So when you place this breakwater, so you can see this the velocity pattern has been changed. The wave is not coming directly, wave is coming here, and the flow pattern has been changed. So, and then the sediment transport also changed in this area. There should be identified, or there should be considered in this model what will be the best location and what will be the appropriate size for this breakwater. It will be like a trial and error. So possible adaptation response to the sea level rise. So the first, we can make the higher setback, and we can lift the house second floor, or we can leave open the first floor. We can keep the breakwater right here, so that the wave will be breaking here. And this is another example. I had a project, is the Boundary Bay. This is the US and this is the Vancouver. So this is a nice house here, is the nice view. And when they built this house, their boundary wall was this height. And after a couple of years, they're expecting the overtopping. So they have started to increase the height of the boundary wall just to protect getting the less overtopping. And there is also the same location. There is another area. They use the temporary breakwater, as I mentioned, shown you earlier. So this main wave will be break here, and the smaller wave will be propagated. They will be less inundated. And this is the resilience housing. So this is the resilience single family housing. It's in Bangladesh. I work over there. And this is a little bit large, so the community can gather here during the storm or the tsunami. And the second floor will be used as a shelter. And this is another type of shelter is there. And this is the resilience housing in Bangladesh. So the conclusion, a hydrodynamic model was developed using a large domain. The regional domain was calibrated for a 2012 Haidegua tsunami at Winter Harbor and the Tofino. For the stability number, there's a counter number. We use less than 1 to keep this stable, and the high density mesh was used close to the shoreline. The combination of the sea level rise by 2,100 and the 500-year probabilistic severe deformation also along the Cascadia zone was considered in the model. Local model for each community was developed using the LiDAR survey information to estimate the inundation zone. Arrival time, the first and subsequent tsunami waves were estimated. Recommendations were made to vulnerable infrastructure relocation and the development of the resilient housing and tsunami evacuation structure in the communities. This is the model we can apply anywhere along the Cascadia zone, or we can develop the different type of model for different area to identify the coastal inundations. I think that's all for my presentation. Thank you.
I think we are ready for some Q&A if there are questions out there.
Dear everyone, your question and answer session will now begin. If you wish to ask a question, please key star, then 1 on your telephone, unmute your device, record your name after the tone, and then press the hash key. If you then decide to withdraw your question, simply key star 2. All questions will be answered in the order received, and you will be advised when to ask your question. All other lines will remain on listen only. You may also submit questions on WebEx. To do this, please click on the 3 dots at the bottom of the screen, then choose the Q&A tab, type your question, and click Send to all panelists. So once again, if you wish to ask a question on the phone, Please key star, then 1 on your telephone, unmute your device, record your name after the tone, and then press the hash key.
And while they're thinking of their questions, I do have one that I wanted to ask. Great presentation, and I like the focus here seems to be on oceanfront property. Does this kind of modeling have an application off the ocean, on a lake, on some other kind of body of water that would benefit from this as well?
Yes, Scott. So this type of model we can apply not only for the coastal Cascadia zone. It can be applied for any water bodies. Yes, it can be applied for the the lake or any waterfront bodies. Yes, it's applicable for everywhere. But at the time, at that location, maybe we have to consider is not like an earthquake, so for like a wind-generated wave of something like that. Yeah, it can be applied for anywhere. Yeah, and yeah.
And I see we do have some Q&A in the WebEx. Our host.
Yes, Adrian would like to know if this modeling technique could be applied to any large body of water, such as the Great Lakes.
Yes, it's possible. The Great Lake, we are working in a project in that area, so that will be applicable for this type of model, and I am working for this project to generate a model. Yes, it's a great question. Yeah, thank you. Yeah.
Thank you. Anne Ariel from San Francisco would like to know, do you have examples of the map products you developed, or how did you present this data to the client or the public?
So we, from the model, we identify the inundated zone. From that inundated boundary, maybe I will show this to the map just a moment. So we have provided this kind of a map. So we say, okay, this is the tsunami boundaries. And we have another map, which is based on the wind wave inundation. So we have provided two maps. This is the map for the tsunami and another map for like a wind-generated waves inundation to the communities. Yes.
Great, thank you. Again, Adrian would like to know, can the model be used for storm-generated waves and flooding, as well as tsunamis?
So, yes. So the tsunami model, there are two models here. The tsunami is the different model, and the wind-generated model is also the different. We have to consider the two models, one for the wind-generated wave and another one is the tsunami, because the wave generation is the different. The wind-generated wave is developed by wind, and the tsunami is developed by the earthquake, is the sea bottom deformation. That is we have done here. We developed the two model, one for the wind and another for the tsunami.
Great, thank you.
Yeah.
All right. Can you hit the last slide there one more time? For our May presentation, we hope you all will join us again. Our presenter will be Tim Alty, and he will be discussing how to extract more value from data by leveraging location intelligence. It'll be on May 13th at the same time slot. We hope everyone will join us for that. And with that, we will close out our webinar today. Thanks, everybody.
Okay, thank you, everybody.
Thank you. Everyone, that concludes your conference call for today. You may now disconnect. Thank you for joining and enjoy the rest of your day.
Thank you.